Hello everybody, it's me, Coach Trigger Looter, signing in for another episode of the Learning C# series, and here we have the third section of chapter 1, Understanding Constants. Past lecture was variables, now we're going into constants, which are actually pretty cool. So let's get into the the reading, shall we? So, understanding constants. There are some scenarios in which we do not want to change the value of a variable after it is initialized. Examples can include mathematical constants, physical constants. So let's see, we have in the mathematical constants, pi, Euler's number, and so on. Physical constants, Avogadro's number, the Boltzmann constant, and so on. Or any application-specific constant, the maximum allowed number of logins, the maximum number of retries for a failed operation, status, code, and many others. C# provides us with constant variables for this purpose. Once defined, the value of a constant variable cannot be changed during its scope. If you try to change the value of a constant variable after it is initialized, the compiler will throw an error. To make a variable constant, we need to prefix it with constant keywords. The constant variable must be initialized at the time of declaration. Here's an example of an integer constant initialized with the value 42. We have to put that in our program. So we have here okay. Oops, sorry. Okay. It is important to note that only the built-in types can be used to declare constant. User-defined types cannot be used for this purpose. Reference types and value types. The data types in C# are divided into value types and reference types. There are several important differences between these two, such as copy semantics. We will look at this in detail in the following sections. Value types. A variable of a value type contains a value directly. When a value type variable is assigned from another, the stored value is copied. The primitive data type we have seen earlier are all value types. All user-defined types declared as structures are value types. Although all types are implicitly derived from the object, type value types do not support explicit inheritance, which is a topic discussed in Chapter 4, Understanding the Various User-Defined Types. Let's see an example here. Integer a data. Okay, for example, let's see. Date time dt equals new datetime. Daytime. What is the daytime here? It's 11th. I think we have to go with 2024. 11th. Today is the 10th. Okay. And now let's see. Console write line dt. Okay, now we build it. Let's build it right here. We build it. Let's start the project. Understand, blah, 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 build success. We run it. What's going to happen? What's going to happen, guys? What is going to happen? There you go. Oh, that's awesome. That's awesome. Beautiful, right, guys? Okay, let's go. Value types are typically stored on the stack in memory, although this is an implementation detail and not a characteristic of value types. If you assign the value of a value type to another variable, then the value is copied to the new variable, and changing one variable will not affect the other. We have integer. Okay, hold on a minute. We have integer. Value type 20, and then we have integer b equals to a value type. It's 20. And value type equals 42. Okay. In the preceding example, the value of a is initialized to 20 and then assigned to the variable b. At this point, both variables contain the same value. However, after assigning the value 42 to the a variable, the value of b remains unchanged. This is shown conceptually in the following diagram. Teacher A. So, integer a, the value is 20, and then you change the value of 20 to 20 with the new value b. So b is a, has the same value 20, and then you change the value of a particularly to 42, but because you set the b to a first in the upper form, b is going to be 20 and a is going to remain with 42. Okay. Here you can see that initially a storage location corresponding to the a integer was allocated on the stack and had the value 20. Then a second storage location was allocated and the value from the first was copied to it. Then we changed the value of the a variable and therefore the value available in the first storage location. The second one was left untouched. Reference types. A variable of a reference type does not contain the value directly but a reference to a memory location where the actual value is stored. The built-in data type, object, and string are reference types. Arrays, interfaces, delegates, and any user-defined type defined as a class are also called reference types. The following example shows several variables of different reference types. A integer 10 the type or name from named list could not be found. Okay. Reference types are stored on the heap. Variables of a reference type can be assigned in the null value that indicates that the variable does not store a reference to an instance of an object. When trying to use a variable assigned a null value, the result is a runtime exception. When a variable of a reference type is assigned a value, the reference to the actual memory location of the object is copied and not the value of the object itself. In the following example, A1 is an array of 2 integers. The reference to the array is copied to the A2 variable. When the content of the array changes, the changes are visible both through A1 and A2, since both these variables refer to the same array. Okay. So for integer, A1 equals to new integer let's see here. A1 new integer array go over there. Let's see, for 2 for 3 integer A2 equals A1 A2 is 42 and 43 integer 0 equals 0. A1 is 0, 43. A2 is 0, 43. Oh, this is A1. There we go. Okay. Oh, wait a minute. Reference types. Oh, this is another. Oh gosh. Okay. Ah. Me and my stupidity. Okay, that's reference types and values is another section. Okay, that's fine. That's fine. That's fine. That's fine. I can change the name later. Can change the name of the repo, I guess. Reference types. Reference types are stored on the heap variable. Okay. Explained conceptually in the following diagram. Stack heap. All right. Okay. Let's keep reading. What the heck? I figured you can see this diagram that A1 and A2 are variable on the stack pointing to the same array of integers allocated in the heap. When the first element of the array is changed through the A1 variable, the changes are automatically visible to the A2 variable because A1 and A2 refer to the same object. Although the string type is a reference type, it appears to behave differently. Take the following example. Okay. Here S1 is initialized with the help literal, and then the reference to the actual array heap object is copied to these S2 variables. At this point, they both refer to the help string. However, S1 is later assigned a new string, demo. At this point, S2 will continue to refer to the help string. The reason for this is that the strings are immutable. That means when you modify a string object, a new string is created, and the variable will receive the reference to the new string object. Any other variable referring to the old string will continue to do so. Boxing and unboxing. Okay. We briefly mentioned boxing and unboxing earlier. In this chapter, when we talked about the object type, boxing is the process of storing a value type inside an object, and unboxing is the opposite operation of converting the value of an object to a value type. Let's understand this with the help of an example. So we have integer. Cool. Okay. The process described. Okay, so in the preceding code, a is a variable of the type integer that is initialized with the value 42. Being a value type, the integer value 42 is stored on the stack. On the other hand, O is a variable of type object. This is a reference type. That means it only contains a reference to a heap memory location where the actual object is stored. So when A is assigned to O, the process called boxing occurs. During the boxing process, an object is allocated on the heap. The value of A, which is 42, is copied to it, and then a reference to this object is assigned to the O variable. When we later assign the value 43 to O, only the boxed object changes and not A. Lastly, we copy the value of the object referred by O to a new variable called B. This will have the value 43, and being an integer is also stored on the stack. The process described here is shown graphically in the following diagram. Okay. Alright, we are here in the next section, nullable types, so I'm gonna pause this a little bit so I can continue with the course. I'm liking this so far. So nullable types is gonna be the last section that we're gonna see in this video, and then next week we're gonna go with the arrays, okay? Give me 1 minute. Okay. Let's go with this, shall we? Nullable types. Reference types have the default null, which indicates that a variable is not assigned to the instance of any object. Value types do not have such an option. However, there are cases when no value is a valid value for a value type too. To represent such case, you can use a nullable type. A nullable type is an instance of system nullable t, a generic value type that can represent the value of an underlying t type, which can only be a value type, as well as an additional null value. The following sample shows a few examples. Nullable. Examples, so nullable integer A, nullable integer B is equals to null. Nullable integer C 42. Okay. You can see that you can use the shorthand syntax T instead of nullable T. These two are interchangeable. The following examples are alternatives for the preceding ones. Integer A, okay, so you can use either this one or this one. Okay, that's fine. Might as well copy that. I think you can run. Fuck. Please. Okay, awesome. And then it has to be. Okay, cool. You can also write it. A integer B integer C 42. All right. You can use the has value property to check whether a nullable type object has a value and value to access the underlying value. If C has value, console write line C value. Okay. The following is a list of some of the characteristics of nullable types. You assign values to a nullable type object the same way you would assign to the underlying types. You can use the getValue or default method to get either the assigned value or the default value of the underlying type if no value is assigned. Boxing is performed on the underlying type. If the nullable type object has not assigned any value, the result of boxing is a null object. You can use the null coalescing operator to access the value of the object of a nullable type. In C#, 8 nullable reference types and non-nullable reference types have been introduced. That is a feature that you must opt for in the project properties. It allows you to make sure that all the objects of reference types that are declared nullable using the T syntax can be assigned the null value. Attempts to do so on non-nullable reference types will result in a compiler warning. Not an error, because that has the potential to affect large portions of existing code. Okay. And with that, we actually struck with the arrays section, and the arrays section. There you go. No. All right. The arrays section is gonna be for a later video. With that being said, guys, I think this course of C# is actually finally taking form. We are reaching places in C# that we actually care about. In chapter 3, control statements and exceptions, I think it's gonna be more of the same, but for now, we are like relearning stuff. As you can see, C# is like more powerful than Python and JavaScript, and you can actually use what you saw and learned in Python and JavaScript into C#, because C# has all those tools that Python and JavaScript have and way more. So when you actually know more about those two other languages, you can actually understand C# better. So yeah, guys, if you like this form of content, please click like, subscribe, and see you guys next time. Bye bye.